energy bar charts and how we use them to represent the role of energy in a physical change. So let's see here. We've utilized heat curves to represent the energy used by a system, okay? So let's say, for example, I have some water, okay? And that water is frozen solid, and we're at a negative 10 degrees Celsius. And then I start heating it. Well, the temperature of that substance is going to go up until we get to the melting point. At the melting point, we're gonna melt, right? So the energy initially is being used to make the particles move faster. Then the energy is used to make the particles split apart, right? So that we can go from a solid to a liquid. Once we finish melting, the energy will be used to make the particles move faster until we get to the boiling point. And at that time, the energy is going to be used to make the particles of a liquid separate so that they can become particles of a gas. And once again, we would see that our temperature would reach another plateau. So again, we can use heat curves to represent how the energy is used by a system. In this case, as some ice is melted into a liquid and then that liquid is then boiled into a gas. Or we can use an energy bar chart, and that's what we're going to be going over today. So what is an energy bar chart? Well, here is what the general chart is going to look like. Okay, excuse me. These are models. Now, what do they show? They're going to show the energy change in a system. Was the energy absorbed or released by the system? So in any example we have where we're making an energy bar chart, we're going to be looking at we'll be looking at the initial energy, right? So what's going on for the temperature, the state of matter, or maybe even chemical energy, although we won't do chemical energy in Unit 3. And then we compare these initial states to the final states. So we get to see how did the energy change in the system. Was it absorbed or was it released by the system? And remember, in the case of the icy hot lab, the system was the water and it was absorbing energy from the hot plate. So again, we're really just tracking, is the energy going to be absorbed or released in an energy bar chart? We also get to see how the energy was stored or used in the system. Again, going back to the heat curve, those points on the graph where we have an increase, a steady increasing line, we know that the energy is being used to increase the temperature, to increase particle movement, right? But here, we're also going to be able to see the thermal energy. So we'll be able to see the temperature. We'll be able to represent, did the temperature go up or did the temperature go down? We'll be able to represent the phase energy. So we'll be able to say, hey, this substance is a solid or liquid or a gas in terms of its energy. And then there's also the chemical energy, which this is when a chemical reaction takes place, is there energy absorbed or released? So one example, again, the chemical energy is going to represent chemical changes. This right here, this is a physical change, okay? This is not a chemical change because when the water melts, it's still water, right? Compare that to this example here, where we take a gummy bear and we drop it into some potassium chlorate and we get this very violent reaction. Here, energy is being released. So we would use an energy bar chart to represent, okay, what is happening to the energy in the chemical bonds of either the potassium chlorate or the gummy bear. Again, everything we're doing right now is more like the water melting, okay? Everything that we're doing is just a physical change, so we're gonna ignore anything chemical change related. We're just dealing with physical changes here. Okay? So again, we won't be using the ECH column. We'll get to that in just a second here. So let's take a look at the different columns, right? We've got the ETH, or the thermal energy column. Yeah, we've got the ETH, and that stands for thermal energy, which is used to represent the temperature, okay? We're just using this column to represent our temperature. Again, if we have a high temperature, we're gonna represent that with more of these bars. And what I mean by that is if the temperature is high, you know, maybe we'll fill out, hold on one second. Maybe we'll fill out, you know, 4 of these, you know? And so we have 4 bars of thermal energy. That'd be a very high temperature. And then maybe the substance we're describing, it cooled off. For example, my coffee sitting in here starts off pretty hot, starts off with a high thermal energy. But after a while, the coffee's gonna cool off all by itself. Its thermal energy will lower. So I would represent that here by just drawing fewer of these bars. So we go from here where we've got 4 thermal energy bars to only having 2 thermal energy bars. So again, that looks like a 4th and 2nd. That's not necessarily what's going on here, but again, high temperature, more energy bars. Low temperature, we should have fewer energy bars, and that's how we'll track the temperature. There's no real rule. It's literally just high temperature, more bars, low temperature, fewer bars, and that's really the only trick there. So that's how we represent temperature. Okay, again, low temperature, fewer bars. The phase energy, okay? The phase energy. This is the energy related to your state of matter. Remember, the different states of matter have different attractive forces within them. Solids, they are very strongly attracted, so there's not a lot of movement. So because there's not a lot of movement, solids they've got low energy, okay? Solids have lower energy. There's less movement in a solid than, say, a gas where there's high energy. So again, solids are low energy. If you have a solid, that's gonna be a low phase energy versus a gas, which is gonna have a high phase energy, okay? So the way we typically do this is we use 1 bar to represent a solid. So let's say I'm talking about an ice cube that is melting, right? So this ice cube is a solid, because that's just, you know, how that works. So in my phase energy column, I would just draw 1 bar, okay, to represent the phase energy, and this would be a solid. Now, a solid melts into a liquid, so the final energy state would be 2 energy bars, okay? I would have 2 energy bars here if I were trying to represent a piece of ice melting. We would be going from a solid, 1 bar, to a liquid, which has 2 bars. And then like it says here, if we were dealing with a gas, that would be 4 bars. So again, phase energy, kind of similar to temperature. Really, we just say, hey, if you've got low energy, you've got less bars, right? Solids just have 1 energy bar. Liquids have 2, because liquids have a little more energy, okay? Hold on. Okay, so, kind of getting to the end here. Yeah, that's the end of part 1. Again, I just wanted to have just a quick video on what are energy bar charts and what are some of their features. Remember, this is just another model that we use to represent the world around us. And in this case, we're representing how energy is used, stored, gained, or